Every lab within the Acceleration Consortium should have active learning and workflow orchestration by 2025. Within all the self-driving labs that have been developed to date, this is one that impresses me the most from the inorganic lab, the self-driving lab at the Acceleration Consortium. This is a frugal twin for electrocatalyst discovery, and it's highly performant. And one of the main things that sticks out to me about this platform is that it was not built with a budget of $10 million and 30 staff, all dedicated to one machine. It was built by one person with some help, but in approximately 3 months and for under $1,000, and it's highly performant. So you can see it here. It's adding different metal precursors for this electrocatalyst, cleaning the electrode. There's some clever design when it came to 3D printed tools that could be kind of interchanged, like interchangeable tool heads. And this really captures that idea of kind of cost effectiveness, modularity, and replicability. On the replicability aspect, this has been replicated at the person's home institution when they went back. My future research centers on real-world active learning for materials. As some examples of what real-world or advanced optimization means, if we take an alloy discovery case, we have multiple fidelities often. You could say this is like running a simulation versus running the actual experiment. Usually there are multiple objectives that come into play. So these trade-offs between different performance properties. There's a mix of continuous and categorical variables, as well as some constraints, some that are linear, some that are nonlinear, and a high number of dimensions. This shows an alloy data set that has 23 unique elements across it. And then this interesting constraint we get with materials in alloys, for example, where usually you won't get more than, say, 5, 6, or 7 unique elements in the material. Now, each of these tasks can kind of be put together as, okay, we have single versus multi for fidelities, objectives, continuous versus this mixed variable setting, presence or lack of presence of different constraints, low and high dimensionality, and again, presence of constraints. And in the most basic case, we'd have kind of the left column for everything. But when we get into some more advanced optimization tasks, we start to see what's needed. There's a tool that I built called Honigumi that lets you quickly create examples of different advanced optimization tasks. So on the left example, you have a simple script, 21 lines. On the right, you have a more advanced script, 62 lines with different syntax, API, all of that. So we get this increase in complexity, and this is something that can pair really well with large language models. Now, I bring that up because by the end of 2025, the target would be for every lab to have 100 or more active learning iterations of real experiments that have been run in the laboratories using some kind of adaptive design technique. And so what I went through before is just kind of pointing out we have the tools, we have these state-of-the-art tools that address these complex materials optimization tasks. Let's figure out how to get those implemented as quickly as possible within each of the labs. And I'll go into a little bit more about labs that are still getting autonomous workflows set up. This gets into the idea of workflow orchestration. Some people may wait to implement an active learning algorithm or have kind of a full orchestration of a platform until all the pieces have been automated. If we flip that, we can have something where the software is the orchestrator, but it's pinging humans. For example, excuse me, human, please move sample 1 from the vial capping station to the powder dispensing station. If we look at an example of that in a particular platform, here we have just a regular Python script. This is our software orchestrator. When we run that, it's going to start our workflow, and it says pausing workflow, execution will continue when it's resumed. This has triggered a Slack notification, which has some information that we've embedded in there. So, for example, if there's a particular sample ID, and we can correlate that with a picture, something that we're looking for. Look at some of the equipment that needs to be handled, kind of link out to these resources that are required. Show what it's moving from and where it's moving to. And then we go and we open this paused workflow run. And if we click resume at the top right here, we'll get the chance to enter in some information, which we've coded into that script. So kind of customizing what you're going to get back from the person in this case. You can click submit. Wait a little bit, and we'll see that the orchestration, or rather the information, has been passed back to the orchestrator. So we go from resuming flow run execution, and we see the information that the user input. If we go back to our Python script that was running, we see it's completed, and we see that it's also passed that back to here. And one of the really cool things about this is it didn't take very long to implement. Again, state-of-the-art workflow orchestration software is out there. Let's use what's there, get human-in-the-loop workflows implemented in our laboratories. So by the end of 2025, the target would be to have every lab with at least one complete human-in-the-loop workflow running that's 24/7. Not saying there's a person in the lab 24/7, but this process is running continually. Now, when it comes to active learning, there's a phenomenon called benchmarking dissatisfaction that appears. This is where you have easy to compute benchmarks that aren't very realistic, or you have realistic ones, but they're incredibly expensive to evaluate and run this benchmarking for. The idea of a Turing test benchmark is something that is cheap to evaluate and is nearly indistinguishable from the real task. I have an example here, something that I worked on, an advanced optimization task. This has 4 objectives. You have some like domain knowledge of what's correlated or anti-correlated with each other, different constraints. And here you can see, this is a web app. You're changing these 23 parameters that are available, including the categorical one that allows for you to control the cost fidelity trade-off. You hit submit and you get your answer here. Now the key part here is each of these iterations took about 30 or 40 minutes on a GPU to run in the initial training data. The way the data set and the models were designed to make this indistinguishable, allows for this call to take place in just a couple seconds instead. And these benchmarks were both, it was easy to make a web app interface like that, but they can also be called programmatically. That particular benchmark, the model, it's about 7 or 8 gigabytes, I think, and so it's a little less portable. But when you host it and allow for this programmatic access, it becomes a lot more usable by different people. And so also by the end of 2025, a target would be for every lab to have one computational or experimental Turing test benchmark that is cheap to evaluate and nearly indistinguishable from running the real task, which requires a large amount of data, and a careful selection of kind of strategy behind what experiments you're running and how many repeats you're running for each experiment. But it's doable and can be expanded in later use. Now with that, in tandem comes the idea of launching an optimization benchmarking competition on Kaggle. Kaggle is a data science kind of competition and data science platform that's really popular, and it's been seeing some increased usage in material science, chemistry, biology. What has not appeared is the idea of bringing in active learning. And part of this is that Kaggle as a platform originally did not make it easy to do something custom. It's very much focused on property prediction and accuracy of predictions. The other issue is that with these cheap to compute benchmarks, let's just say like an analytic function, there's not a lot of mystery. You already kind of know what the answer is, and it becomes a little harder to have a fair competition going to that. With self-driving labs and the generation of these Turing test data sets, there's a change in the Kaggle competition platform to allow for really customized evaluations of performance within the last year or two. There's a really ripe opportunity for having this kind of materials discovery benchmarking competition there. On the research side for active learning, there are some outstanding research challenges. One in particular is multitask optimization. In this example, you say maximize the ceramic membrane strength, and you have two different material systems, two completely separate experimental systems that this coating is being run on, and these tasks are correlated with each other. They take approximately the same, they have the same search space, input parameters. How do we deal with modeling that? And nearly every multitask kernel or a lot of these techniques assume a common mean in the kernel. And what that means is if you are far away from the data that you have, you'll end up with extrapolation that's nearly identical. So here we have the true function for task B up top and for task A on the bottom. And if we look at this gap here, when we're far away from the data on task B, it extrapolates to 0, same as with task A, even though the true function is much higher. This is a common limitation in a lot of the built-in algorithms, and is just one example of some of the outstanding research challenges in real-world materials discovery tasks. Some different challenges that may come up, this idea of buying versus building and trying to integrate multiple devices together. Some other challenges, we have this tension between research outputs and service or more infrastructural outputs. Time to create a system versus documenting it really well, making it replicable, robust. Some labs needing really tailored solutions because of the discipline or the specific workflow versus trying to align on universal conventions, reduce unnecessary and ineffective redundancy. Next comes this autonomy level versus level of human intervention, which I talked about a bit. And then we also have equipment cost versus the research fidelity, which I touched on with the electrocatalyst discovery problem. Finally, we get into sort of open sourceness and closed sourceness, and this tension between making our results, our designs open and available versus keeping certain things closed and looking at the commercial aspects as well. In terms of an equitable and inclusive environment, for me, it's about seeking talent from underrepresented groups from the very beginning, looking to have remote participation options and seeking funding for bringing people who have geographic or financial barriers to engaging, and then really looking at the existing initiatives within the AC, doing grants, participating in meetings, supporting different events.